Okay, now we consider another important concept that we already know in the case of single random variable. Now we extend that to two random variables. We see the conditional distribution and density functions of the random variables x and t. Let A and B are two events, then the probability of A given B is equivalent to probability of A intersection B divided by probability of B. So this is called the conditional probability of A. Conditional probability of A given B has been occurred. So this is the fundamental definition of the conditional probability. Now we relate these two events. Let this event A as x less than or equivalent to x, and B is another event that is associated with the random variable y. Okay. So therefore we can write the probability of this x less than or equivalent to x given y less than or equivalent to y is equivalent to probability of A and B, that is x less than or equivalent to x and y less than or equivalent to y divided by probability of y less than or equivalent to y. So we already know that this probability, that is the probability of x less than or equivalent to x and y less than or equivalent to y, is equivalent to joint CDA. And the denominator is the marginal distribution of the random variable y. So it can be written as fy of y. So provided that this fy of y is not equivalent to 0. So here this ratio fxy of x comma y divided by fy of y is called as conditional distribution function. That is the probability of x less than or equivalent to x given that y less than or equivalent to y has been occurred. So this we denote as f x given y x y. See this notation: probability of A given B, probability of x given y equivalent to y, or y is less than or equivalent to y. So this is the notation of this. So this fx of y x comma y is equivalent to this one. This is called as the conditional distribution. This is called the conditional distribution of the random variable x given y less than or equivalent to y as occurred, or y is taking values less than or equivalent to y. We can say that it is the probability of the random variable x that takes values less than or equivalent to x given that y is taking values less than or equivalent to y. That can be obtained from this. This indicates if you know the joint CDF and the marginal CDF, we can evaluate this. Similarly here, if you change the role of A and B, then probability of B given A is equivalent to probability of A intersection B divided by probability of A. Probability of A not equivalent to 0. Therefore, in the same manner, we can write this fy x, this is yx is equivalent to fxy x comma y divided by fx of x. So here also this is fx of x must not be 0. So therefore, we can write this fxy of x comma y. See, all these relations are similar. We already studied. We simply replacing a with the event x less than or equivalent to x, b with y less than or equivalent to y. That is the difference. This fy of x yx into fx of x, which is equivalent to fxy of xy into fy of y. Is it right? So from the previous equation and this equation, we are writing this. We are equating fxy of x comma y. Fxy of x comma y is fx of x into this. Okay, from the previous equation, this fxy of x comma y is this one. So from this, we can write this fyx yx is equivalent to fxy xy, and this is fy of y divided by fx of x. What is this? This is the well-known Bayes theorem. Follow. Similarly, we can write f x given y, x comma y, and the same equation. This is the Bayes. We change the two events and we consider one more relation. You see the meaning of point condition. Now let C is equivalent to random variable x lying in between x and x plus dx, where dx is a small value that is tending to 0, and let d is another event where the random variable y is lying in between y and y plus d. So if you let x is a continuous random variable and y is a continuous random variable, okay? So x less than or equivalent to x less than or equivalent to x plus dx is equivalent to simply x equivalent to x. Similarly, this is y equivalent to y, because we are letting this dx and dy are tending to 0. They are very small values. So they are very small. If x and y are continuous, probability of x lying in between x and x plus dx, y lying in between y and y plus dy is simply equivalent to x equivalent to x, y equivalent to y. So here we find the probability of the random variable y given x is taking a value small x. Similarly, the probability of the random variable x given that y is taking a value y, okay, one single value. So that type of conditional probability is called as a point condition probability. That is, we are finding the probability of one random variable given that other random variable is taking a single value. Understood? Here consider probability of the C and D. So this can be written as probability of x less than x less than or equivalent to x plus dx and y less than or equivalent to y plus b. Okay. Follow? So this can also be written as fxy of x comma y plus fxy x plus dx comma y plus dy, we already know it, minus fxy x comma y plus dy minus fxy x plus dx comma, understood this? Probability of the random variable x lying between x and x plus dx and y lying between y and y plus dy can be written like this. Now we consider this fxy x comma y plus fxy x plus dx comma y plus dy minus fxy x comma y plus dy minus fxy comma x plus dx comma, and divide this with dx dy and let dx and dy are tending to 0. Follow? So this is equivalent to dou square fxy x comma y dou x dou y. So this above equation, when dx and dy tends to 0, is equivalent to partial derivative of fxy of x comma y twice. So here we already know that dfx of x dx can be written as fx of x plus dx minus fx of x by dx as limit dx tends to 0, is it? In the same manner, this divided by this, when dx tends to 0 and dy tends to 0, is the partial derivative of this with respect to x and y. So here, partial derivative of this fxy of x comma y is equivalent to fxy of x comma y. Is it? Follow this. So therefore, probability of x less than or equivalent to x plus dx and y less than or equivalent to y plus dy is equivalent to this is how much? See, what is this value? This value is this, is it? See, the numerator here is equivalent to this, okay, divided by dx dy. This divided by this is equivalent to this. So can I write this as, that is, this approximately equivalent to fxy x comma y. Is it right? I am using this equation. The numerator here is the probability of this and this. Then we can write probability of the random variable x between x and x plus dx, y less than or equivalent to y plus dy is approximately equivalent to fxy x comma y, this is dx. Is it right? See, this relation is similar to that of the relation that we already derived. Okay. So probability of x less than x plus dx is equivalent to fx of x into dx. So what we call this as a probability element of the random variable x. The probability element of the random variable x is this one. We already derived in the case of one random variable. Now this is the extension of this. So here we consider two random variables, then the probability of this event and this event is equivalent to fxy of x comma y dx dy. Understood this? So here it is called the probability element of the random variables x and y. This is the probability element of the random variable x. In the same manner, this is the probability element of the random variable x and y. Now we consider probability of y less than y less than or equivalent to y plus dy given x is lying in between small x and x plus dx. See, I am following a step-by-step procedure. At the end, we come to know what we are doing. Okay. I have understood the previous derivation. We have shown that the probability of the random variable x lying in between x and x plus dx, y lying in between y and y plus dy is equivalent to fxy x comma y into dx dy. Now we are considering another probability. This is the conditional probability. So here, this is equivalent to this can be written as probability of x less than or equivalent to x plus dx and y less than or equivalent to y plus dy. That is probability of A intersection B, which is nothing but probability of B intersection A. Because intersection operation is commutative. Probability of A intersection B is equivalent to probability of B intersection A. Actually, we have to write this as probability of y less than or equivalent to y plus dy, comma x less than or equivalent to x plus dx. That can be written in this. Divided by probability of x less than or equivalent to x plus. So this can be written as, see, fxy x comma y divided by, this is how much? See, can I write this as fx of x into dx? Because probability of x less than or equivalent to x plus dx can be as fx of x into dx. What is this fx of x into dx? The probability element of the random variable x. Okay. Understood this? Now, what about this? So can I write this as fy why I am taking y here? Because both y and x are taking a single value. Even though we have written y less than or equivalent to y plus dy, but dy and dx are very small. So therefore, I can write it as fy x, and this is see, we already assume this c is equivalent to x less than or equivalent to x plus dx. Is it right? See the previous pages. Okay, we assume the event x less than or equivalent to x plus dx is c. Therefore, can I write this as rho c this, okay, minus Fy of C is it right? Can I write this as this? See, I will write probability of y less than y less than or equivalent to y plus dy can be written as Fy of y plus dy minus Fy of y. This is the fundamental property of the CDF, is it? Probability of y1 less than y less than or equivalent to y2 is Fy of y2 minus Fy of y1. Now here I am conditioning this. Okay. Probability of this given that C has been occurred. Okay. So therefore this given that C has been occurred, this given that C has been. Is that right? So therefore this probability, a probability of this conditional event, probability of this given that x is lying in between x and x plus dx can be written as Fy of this minus Fy of this. Understood this? See, this step is very simple. We use the fundamental relationship between the probability of this event and the distribution function. So this is the distribution, marginal distribution. This is a conditional distribution. That is the difference. See, in the previous slide, we obtained this relation. This divided by this is approximately equivalent to fxy of x comma y. Is it? Is it right? So as dy tends to 0, okay, what is this value? See, this is the derivative of this. Can I write this as d Fy given C? This is how much? Y given C. Is it right? Here I can do one thing, approximately. Why approximately? We are letting this dx or dy is tending to 0. We already assumed it. So this is the derivative of this. As we are dividing this with this. Now, this equivalent how much? Can I write this as Fy given C? Now, this divided by this value divided by dy is equivalent to this much. Is it right? What is the probability of x lying between x and x plus dx, y and y plus dy? I have understood up to this point. Is it clear? Up to this. Now, probability of this x lying in between x and x plus dx, y is lying in between y and y plus dy is equivalent to, see this slide. See, this is equivalent to fxy x comma y dx dy. This is fxy x comma y dx dy. Is it right? Now, can I write this as dy and this? We will simply bring this side. So therefore, I can remove this here. But what is this value? This divided by this. see, this value is equivalent to this. Is it right? You compare this and this. Can I equate this numerator to this numerator? Both are same. See the equations. Can I equate this numerator and this? Can I equate those two? Follow this. Otherwise, this probability can be written as this into this. Is it right? The numerator can be written as Fy given C to Y given C minus, this is, I think here Y plus D. Minus Fy given C, Y given C into Fx of x dx. This is how much? This is equivalent to probability of x less than x, x plus dx, y less than y plus 2. See the above equations that we have written. From those equations we can simply write this equivalent to this. Now, this can be written as dy is it right? Divide with dy on both sides, no change. Understood this? So therefore, what is this? This value this minus this divided by dy. We already obtained. Y given C into Fx of x dx is equivalent to, see, what is this value? This value can be written as Fxy of xy dx. Is it right? So therefore, this implies Fy of C, y given C is equivalent to, see, dx get cancelled and we have Fxy x comma y Fx of x. Is it right? And we obtain the relationship between the joint PDF. So this is a conditional PDF. So finally we arrived at Fy given C, this y given C is equivalent to Fxy divided by Fx of x. Is it? Here this Fx of x must not be 0. But what is C here? We define the C as x less than or equivalent to x plus dx. See, here our assumption is dx is very small. So if dx is very small, can I write this as x equivalent to x, probability of x equivalent to x, because x is taking the single value x. So therefore, I can write this as fy of x, y x is equivalent to fxy of x comma y. This is fx of x, given that this fx of x is not equivalent to 0. So this equation is similar to that of that we already derived this one. Joint distributional density functions of y given x is equivalent to x. Follow? We obtain the joint distribution and density functions of the random variable y given the random variable x is taking a single value. Why? Because x is lying in between x and x plus dx. But we are assuming dx is very small. So that can be considered as x is taking a single value. So therefore, this is the probability or the joint density and distribution functions of the random variable y given x is taking a single value. Understood this? See, this relation is written directly from the definition. So that is, in point conditioning, we are finding the density or distribution of the random variable, one random variable, given the other random variable is taking a single value. So these derivations are very important. So these two relations are very important for us. So where we use these conditioning events or conditioning density and distribution functions. So there is one important concept of one important area. So in almost all the fields of science and technology, we need to use this. So that is the failure to find the failure rates in the real-time problem, we use the conditional density and distribution. So we already know that fx of x is equivalent to integral minus infinity to plus infinity fxy x comma y dy. Is it right? What we call this? This is a marginal density function. So from this you can write minus infinity to plus infinity. See, from the previous equation, what is fxy of x comma y? That can be written as fy x, this is yx into fx of x dy. Is it right? So from this, can I take this fx of x outside? Can I take this fx of x outside? Because we are integrating with respect to y. So this fx of x get cancelled. So from this we can write integral minus infinity to plus infinity fy x, this is yx dy is equivalent to, is it right? Follow this. So what this indicates, that is the conditional density function will also satisfy the same properties. Okay. So therefore this is also a valid probability density function. because the area under this function is equivalent to 1. That indicates it is a valid probability density. But we call this as the conditional density function. See, we have the density function, joint density function, and this is the conditional density. Here you can also write the previous equation as this is fx of x. Is it? This is the previous equation. Similarly, this fx y x comma y is equivalent to, here I am changing the role of x and y. Okay, then you will get xy, and this is fy of y, given this fy of y is not equivalent to. So these relations are important.